Okay, so we're going on to chapter 7, stuff like that. So, but in fact, what's actually going to be happening is we're going to do part of chapter 7. So this is all that we got through yesterday in lecture. So that's what I'm going to cover. We're going to come back to here. So if you're taking the Organic Chemistry 2 with me, this is where we're going to start, and we'll go through the whole chapter because we're actually going to be starting to get into some proper reactions. Okay, so but that's what we've got up to this point. We've been learning a lot of background, but so now we're going to start hitting reactions pretty hard. Okay, and so what we're going to be doing, so we're talking about proton transfer steps. Okay, so we touched on this with acid-base chemistry, but it's the reactions are going to be very, very, very similar. They're all going to all of the ones that we're going to touch on today are going to be no different than what we learned in chapter 6. Okay, we're just applying them slightly differently. Okay, and so what's going to happen is, right, so we talked about these proton transfer reactions, right? So here we've got plus HCl, okay, going to right, HOH plus Cl minus, okay. Okay, and so what's happening is, right, this negative charge, right, is going to be attracted to the partial positive on this polar covalent bond, right? So again, right, we're going to take those lone pairs, make a bond to that hydrogen, right? It's going to be attracted, but the hydrogen only needs one bond, right? So these two electrons are going to get pushed onto that chlorine, okay? And so so this set of lone pairs becomes that bond, okay? This bond becomes this extra set of lone pairs, okay? This same stuff from chapter 6, okay? But what you have to remember is, with these reactions, opposites are going to attract, likes are going to repel. So if you have a negative charge here, it's going to get attracted to anything that has even a partial positive on this side, on this molecule, okay? Now we're going to talk a little bit about Lewis acids and Lewis bases. Okay, so with that, we're going to just touch on this a little bit. What Gilbert Lewis did is he said, okay, Bronsted-Lowry is too constricting because we're only looking at hydrogens, and for the most part, that's what we're going to be looking at. But really, what we're looking at is things that have. It's really going to be the flow of electrons. Okay, so here, right? So this base here, okay, has a lot of extra electrons. Okay, so it has electrons to give, to donate. Okay, this hydrogen here, because it's lacking, it has a partial positive charge. That means it's lacking electrons. Okay, and so it's going to be able to accept those electrons in to make the new bond. Okay, so if you're a Bronsted acid, okay, you're also a Lewis acid. If you're a Bronsted base, you're also going to be a Lewis base, but for Lewis base, it's a much larger group because there's a lot of different elements other than hydrogen that can move around, stuff like that. And so, but the concepts are still exactly the same, and stuff like that. And so, you're always going to go from electron rich, your Lewis base, to the Lewis acid, okay, which is electron poor, okay, because that's why it's got the partial positive there. Okay, that's where it's going to be, but it's still going to be a lot of this lone pair to bond to lone pair situation, okay, stuff like that. And so one of the ways that we can make these, right, so the whole point of organic chemistry is to make carbon-carbon bonds, okay? So if we're going to do this, okay, if we're going to make have the carbons have a lone pair that it can go and attack something with, right, we have to be able to stabilize it, okay? And it's a little bit more difficult to do than other sorts of things with negative charge. Okay, so let's say you've got this compound here, and you have a positive charge. Okay, so it has 3 bonds, right? So this is called a carbocation. Okay, the carbo for the carbon, right? And cations, right? They're positively charged. Okay, so it's a right? So it's a carbon with a positive charge. Not too bad. Okay, so here, right, so if it has a lone pair, Okay, now with up here you did the formal charge, right? So you'll have plus charge. Here, if it has a lone pair, it has a negative charge. Okay, so here we're going to call this a carb. It actually ends up being, a carb anion, right? We don't want to say carboanion, although I suppose you could. It's usually combined a carbanion. This is actually all one word, by the way. So again, for carbon, negative. Okay, so it's a carbon with a negative charge. So carbanion has a negative charge. Carbocation has a positive charge. Okay, but what we're going to do is for this one here, what we're going to do is we're going to put some sort of metal cation here in order to be able to stabilize this. So there's three primary ways of doing this. Okay, the first one would be, let's say you've got this CH2. What we're going to do is we're going to have a lithium here. Okay, so this is just sort of, you usually just call this to be an organolithium. I know, they didn't have a real fun name with this, okay? The way that you know that this has a negative charge is that if you look in the periodic table, lithium is in that first column. It's in the alkali metals. So it's typically going to want to have a positive 1 charge, right? To balance that out, right? It's there to balance out the negative 1 on the carbon, right? So carbon effectively is working like this. Okay, it has a set of lone pairs and it's negatively charged. Okay, so another way that you can do this, okay, and so for here it doesn't matter that it's a benzene, okay, you can put a magnesium bromide or magnesium chloride on here, okay, and these are typically called Grignard reagents. Grignards. Okay, and again, what we're doing is this is essentially putting a set of lone pairs in a negative charge there. Okay, now why do we have the bromine here? We only had lithium. Well, if you think about it, again, that carbon, right, is going to have a negative 1 charge. Magnesium, it's in the second column. It's an alkali earth. Those typically have a +2. Okay, so but we're out of balance, right? Negative 1 and a +2. So to balance that out, we put in the bromine, okay, and that'll balance it out. Okay, and so with that, so -1, -1 to balance out the +2. Okay, but the last one that's typically used are these organocoppers. Okay, now the thing is, you usually have with the coppers, you usually have two carbon groups, independent carbon groups, and usually they're symmetrical, stuff like that. But there's actually 2, and it turns out copper is a really weird element. It's just in organic chemistry, it does some crazy things. It turns out that right, each one of these carbon groups is going to have a -1. Okay, because again, what's happening is you have 2 of these CH3s with a lone pair and a negative charge on each one of these. So you're going to have 2 of these. Okay. Turns out the copper has a +1, right? And so to balance that out, you're going to need usually have a lithium in here, so that's also a +1. This is called a Gilman reagent. Okay. So about that, it's a little softer than Grignards and organolithiums. So about that, but again, we'll talk about that later. But effectively, what these are doing is stabilizing a carbon with a lone pair and a negative charge. Okay, so they're making it look like the hydroxide, right? So you have a lone pair that you can make a bond to. Okay. Okay. So if we have something like this, okay. So with this, so if we have our, if we have our benzene, so we have our Grignard reagent here. Okay. If I have this, you have to realize that this is essentially has a negative charge and on there, so it's acting like that. Okay, so if we react this with water, right? So with that, so positive, negative, positive, right? So with that, so this negative charge is going to be attracted to that positive charge here. Okay, so that's going to rip this, right? These lone pairs are going to make a new bond with that hydrogen, right? So with that, so we only do 1 bond, right? So we're going to take those 2 electrons and push those onto the oxygen. So you're going to make benzene, the world's most expensive benzene, right? So that hydrogen is going to go there, plus OH minus, right? So these 2 electrons from that bond there turned into these. Okay, so this bond there turned into that there. So these that lone pair of electrons there turned into this bond there. Okay, it's no different than what we were doing with hydroxide and HCl. The reaction is the same. It's just the players have slightly changed, but the reaction still works just fine. Now, the other way that you can do this, okay, now instead you want carbon, if you want hydrogen, you can't just add sodium hydride, NaH. Okay, yes, it does have that, but it turns out it doesn't. It actually acts as a very efficient base as opposed to a nucleophile. We'll talk about that later. So that doesn't work real well. Okay, so what you do is you have compounds called lithium aluminum hydride. Okay, the other one is sodium borohydride, and each one of these, right, is essentially four bullets, and they're effectively delivering an H with a set of lone pairs. So now you can add a hydrogen to your. You can actually add in a new hydrogen bond, right? Because now you've got that a hydrogen with a set of lone pairs. Now it can go in and make its own bond. Okay, so for that, each one of these is going to, right? So it has 4 hydrogens. So it's going to, each one of these has 4 hydrides. So as this one has 4 bullets that it can spend. Okay, so what you can do, okay, is not just take. So you can do this not just with hydrogens. You can do this with anything that has a partial positive, right? So if we have something like this, right? So if instead, let's say we have, so we have methyl chloride, right? So again, we're going to have, the chlorine, right? It's more electronegative than carbon, right? So you can have a negative, partial positive, right? This is still going to be, right, so let me draw this out. Okay, let me draw out these hydrogens. Okay, right. So it has the 3 hydrogens around it here, but these lone pairs are still going to get attracted to that positive charge here. It doesn't matter that it's a carbon. Okay, it's still going to be attracted to it. So it's still going to want to make a bond here, but carbon already has its 4 bonds, just like hydrogen had its 1 bond. It's got to shed one. It's got to get rid of it, or else it's going to have too many bonds. So what does it do? It does the same thing that hydrogen and HCl did. It pushed those electrons up onto the chloride. Okay, so you end up with HO, right? CH3, okay, plus Cl minus. Okay, it's no different than what we were doing up here. Okay, we have the negatively charged thing attacking the positively charged thing, and then we're pushing that away. We're pushing electrons onto that, pushing them away to get a group. Okay, stuff like that. So this right here, okay. So a couple of different things. Okay, so this reaction here is called an Sn2 reaction. Okay, it's what's called a substitution. Okay, that's what the S stands for, because you're substituting this group for that group. On this carbon, it's just a CH3, but you're substituting it. Okay, this group here, that's called the nucleophile. Okay. Okay, it's the bond that wants to make. It's the one that's doing the attack. It's the one that makes the new bond. Okay, this group here is called the one that leaves the molecule. This is called the leaving group. It does exactly what the name says. It leaves. Okay, the chlorine left. That is the leaving group. They're typically going to be electronegative, right? So with that, and it's bimolecular. So with that, so it's a nucleophilic. It uses a nucleophile. Okay, that's what the N stands for, and the 2 means it's bimolecular. There's the rate determining step, as it turns out, is these 2 things smashing together, because there's two molecules involved in that rate determining step that is considered bimolecular. Okay, so with that, so for leaving groups, they're typically going to be weak conjugate bases. Okay, so if you had strong bases, so chlorides, right? So chloride is a right, HCl is a strong acid, so that means the chloride is a weak base. Not too bad. Same thing with bromide, same thing with, right, so if you had sulfate, or sulfuric acid, right, its conjugate base would be a really good leaving group, okay? But HF is a weak acid. That means it has a fairly strong conjugate base, okay? So that means that fluorine is a really pretty terrible leaving group, okay? That's why Teflon, which has all the, in its it's an alkane polymer. All the CH bonds have been replaced with CF bonds. The reason why it's so chemically resistant is because one of the reasons is because that CF bond is so strong and it's a really bad leaving group. Stuff like that. So, okay, so with that, so nucleophiles, okay, so with that, so this is, right, so this is, this is positive loving, okay, right, nucleophile, it's the same root as, it's positive, right, so same root as the nucleus, right, where all the positive charges in the atom, and phile is loving, right? What things love, what things are attracted to positive things? Well, negative things, right, because opposites attract, okay, so if you had an electrophile, a negative loving thing, right, so what attracts, what's attracted to negative things? Positive things, okay, so get that. So, but you're going to need to have a lone pair on your nucleophile. Okay, that doesn't mean that there aren't going to be lone pairs on this other molecule, but you definitely need to have a lone pair on your nucleophile because you need those things. You need those electrons to make the bond, right? To make that new bond. Okay, so for that, typically they're going to have either they're going to have negative character to them, right? They're going to either have a full negative charge or they're going to have a partial negative charge. Okay. So with that, but the reaction is the same, right? So with that, so this proton transfer reaction, right? We're making a new bond here to what had the positive charge, and you're kicking the electrons onto the neighbor. Same thing here. You taking the bond from your nucleophile, attacking the thing that's positively charged, and then kicking those electrons onto the neighbor. The reaction is exactly the same. The mechanism is exactly the same. Okay. So with that, so don't think of them any differently. Okay, so if we had these reactions, right? So with that, so if we had, right? So we had O plus bromide here. Okay, so which is our nucleophile? Well, it's going to be here, right? That's where the negative charge is, right? We have a lot of extra. Oh, there should put. Sorry, I forgot to put in lone pairs. Here, so with that, so right, so this is going to be a nucleophile. That's the thing that's negatively charged. It's a pretty good hint that that's going to be a nucleophile. So then the question on the other side is, do we have a polar covalent bond? Okay, yeah, we do. We have it right here, right? So bromine's pretty electronegative, right? Especially compared to carbon, right? So our carbon here is going to be, it's going to be positively charged, right? So I'm going to put our dots here, right? So that means that one of these lone pairs is going to get attracted to it. Right, and don't forget this carbon has its full complement of 4 bonds, right? So as it comes in here, as it tries to make a bond with this, right, we have to get rid of one, and what happens is, right, it's going to push it onto the neighbor. It's going to push the electrons onto the leaving group, okay? And so what you're going to end up with is your 5 carbon piece here, and then your leaving group, or then your nucleophile attached below or attached to it. CH3, right? Because these electrons are making the bond here, and this methyl group is just coming along for the ride. Okay, so you come in here, you make a bond from here to here, right? So with that, right? So with that, and all the rest of the molecule comes along for the ride, and then you make a Br minus. Okay, so you make, all right? So that bond there, those 2 electrons here become this 4th set of lone pairs. Okay, so here's mine, some professors you have to show it all. I'm mostly concerned with the organic molecule. If you show this, great, but I'm not going to take it off if you forget to put that in. My concern is the main organic molecule. Okay, so here we go. So we have this. Okay, so when you see this, you're looking for where's your nucleophile. Okay, well, we have a Grignard reagent here, so what this is saying is we effectively have a set of lone pairs on that carbon, right? So on that carbon, right, a nucleophile. So then we come over here and say, okay, where's our polar covalent bond? Well, it's right here. There's a partial positive here, partial negative there, right? Put in the lone pairs. Okay, so this is going to attack here, and again, we have too many bonds, right? So with that, so if we're making a bond, we have to break a bond, so we're going to push those there. Okay, and so what we end up with is, right, so there's a, right there, and then we're making that new bond to the triangle, like that, okay, plus Br minus, like that. Okay, so like that. So, but again, it's the negative getting attracted to the positive. Okay, and then in making this new bond, so we're going to break it. Okay, so there you go. So right now we're going to skip 7.3. That was into some very technical things as far as the naming of making and breaking bonds. So we're just going to skip it. Okay. Now the alternative way, and it turns out that you can have your nucleophile not just attack here, but actually attack next to it. Okay. And these are what are called elimination reactions. Okay, and these are typically going to be E2, or there's also the corresponding E1, stuff like that. But when you see this, you instantly need to think new pi bond. Okay, stuff like that. So, and 90% of the time, it's going to be a new carbon-carbon double bond. Okay, now, so with that, so the way this works is, right, so you need a leaving group, okay, but you need to have involved two carbons here on where the molecule that gets attacked. Okay, here we've only dealt with one carbon. Okay, now we have to deal with two. And so what ends up happening is, wherever your leaving group is, okay, so in this case is a bromide, okay, what ends up happening is you're going to throw in a base, okay, so do your classic base. And so what ends up happening is instead of attacking right here, okay, what happens is it actually grabs one of the hydrogens that's next door. Okay, now this, again, we're making a new bond here, so we need to figure out what to do with these electrons. Okay, so what it actually does is it actually, instead of pushing them onto the carbon, because carbanions are pretty unstable, what it does is it actually puts them down here in order to make a double bond. Okay, and doing so, again, now this carbon's freaking out because it already has its 4 bonds. It needs to break one, so it, again, pushes away that leaving group, and what you end up with is, in fact, right, so there was already hydrogen here, right, so you end up with a double bond. Okay, now you could attack here, right, and there's no reason why you couldn't. Okay, now that would collapse down and do the same thing, but that molecule that would be formed would be this. Okay, these two are the same molecule. All you got to do is rotate this, and it turns into this. So really, we just need to show one of them. Okay, so be careful with cyclic compounds, because if you just rotate them, they can sometimes be equivalent, and you get chains can sometimes happen. Now, why I said 90% of the time you can do this, because the other thing that you could do, okay, if you already had a double bond there, and you already had, say, your leaving group here, you could again add base. Okay, is there a hydrogen next door? Not on it, not this one, next door, right? Because you have to have two carbons to be able to make the double bond, okay, to make the new pi bond. Okay, yeah, there is. So we're going to add this here and then collapse that down. Well, we didn't do anything with those double bonds, right? Just like we didn't do anything with this single bond. Okay, and so what ends up happening is you end up with a triple bond. Okay, so this is a classic way of making a triple bond plus. I'm sorry, I forgot to show that the leaving group, and then the leaving group goes away, and so you end up with H2O plus Br minus. Okay, so this is a classic way of making a triple bond, is to start with this double bond, and then have H on one side and a leaving group on the other, hit it with base, and then it collapses down to that triple bond. Okay, but most of the time, 90% of the time, when you see this, it's going to be making a carbon-carbon double bond. Okay, but again, it's going to be something electron rich, which is going to be attacking something electron poor. Okay, stuff like that. So it just so happens to be next door. Okay, and stuff like that. And so again, on these reactions here, where it's right, so I'm actually going to write Sn2, at least to start with, so that you know that what I want is the substitution. Right, we are substituting our nucleophile for what the leaving group is. We are substituting our nucleophile for what the leaving group is. Okay, that's the substitution. The elimination, I'm going to write that this is an E2. Okay, you have to, alarm bells need to go off that yes, indeed, we're going to make a new pi bond. Okay, and so, so we have OH minus, Okay, and so what we need to do is to say, okay, here's our leaving group, right? Here's our base. All right, nice. I'm going to tell you, right? It's E2. Okay. Now, what you have to do is you have to say, okay, are there hydrogens adjacent to it? Well, there are hydrogens here, so that's good. That means we could part of the time it's going to be on this side. Okay. The other side, now the other possibility is, ooh, what if we do it on this side? Well, there are hydrogens here, right? Only one bond shown, right? So on this one, right? So that means that there's 3 hydrogens. So we can do it this side too. So there's in fact two possible products. Okay. If you go on the red side here, your product ends up going right because when you rip this away, right, that's going to collapse down and kick that away. You're going to end up with this product. Okay. If instead you grab this hydrogen, right, those are going to collapse away and kick that off, and you're going to end up with this product. Okay, plus Br minus. Okay, but this is where the original leaving group is going to go, and so you have to look on both sides. Okay, to see where this. As long as you've got a hydrogen there, okay, you had a hydrogen here, so we can make a double bond there. We had a hydrogen here, so we could make the double bond there. We're good to go. Okay, now there are rules for doing this. These are called Zaitsev rules. We're not going to go into that yet. Okay, we're not going to worry about it in the course. You just need to recognize that these are the 2 different products. You're going to go, typically it's on either side, so with that, so of the double bond. Okay. So there you go. Now, next thing that we can do, okay, is we don't necessarily have to hit something positive that has a leaving group on here. Okay, so let's say we had this. Okay, I throw that in there. Okay, again, this is a polar covalent bond, right? So we're going to have a partial positive, partial negative. So this negative charge here is going to get attracted to it, right? So these lone pairs are going to come in here, but this ketone, right? It already has its 4 bonds. So what have we done? Right? So what do we usually do? We usually, when we're trying to make this 5th bond, right, we push electrons up onto the neighbor. Now we can push this pi bond, right, up on here. Okay. The nice thing is, okay, that oxygen is still tethered. It's not really a leaving group. It hasn't gone away. It's still tethered to the molecule, right? So ends up being a positive charge, right? CH3. Okay, so this can happen. It's still going to be the same thing, right? So you end up making this. Okay, so you have something negative attacking the partial positive, and then pushing. I have too many bonds. So we're going to pushing the electrons from one of the bonds up onto something else, onto an adjacent atom. And it turns out here you're going to want to put it up. You're going to want to push the those electrons up to the oxygen, because if you're to push it here, you'd have to break a carbon-carbon bond, which is pretty tough to do. Same thing on this side. It'd be pretty difficult to do. Okay. Okay, so it doesn't matter. Usually it's a C double bond O. 98% of the time it's going to do. But you could do it where you let's say you hit this with acetonitrile, which is that. Okay. Again, you're going to have a partial positive, partial negative, right? If this were to attack, say here, right? Again, we're going to push one of those sets of electrons up to make sure we maintain the 4th bond, so you'd end up with C double bond N, right? So this set of lone pairs is going to be this new set here, and then you're going to end up with a CH3. Okay, it turns out that this is going to have that nitrogen is going to have a negative charge on it, so like that. But it's no different than what we've been doing before. A negative attacking a positive, okay, and then to get rid of a bond is formed, right? So we need to we need to push the electrons away to a neighbor, stuff like that. So to maintain the octet on the carbon. Okay. Now you have to be careful, because as an aside, what can happen is so for here, I'm going to do this bottom one first. Oh, yeah, hold on. Let's do this one. So let's say you have, okay, so let's say we start off with this, and I say, okay, we're going to do, instead of the ketone, we're going to do the acid chloride. Okay, so again, we're going to have partial partial positive, partial negative. Now, you can say, well, if I attack, so I'm going to attack here, well, I could just push that away. Turns out that what actually happens is these get pushed up. You're going to push away the those two electrons up into the oxygen. That's actually easier to do because you're not actually breaking a bond, right? So that you're not, you're not. I should say, well, I guess technically you are, but you're not chopping away one of your, part of your molecule. Okay. So it forms what's called the tetrahedral intermediate. We'll talk about this more later, but again, you're going to have this. Okay, what you want to do, okay, and then your other methyl group ended up going here. Okay, stuff like that. So what you ended up doing was, right, stuff like that. Oh, there's a negative charge up here. Okay, now the carbon where you attacked. Okay, is there a good leaving group? There is. There's a really nice leaving group here. Okay, so what ends up happening is this collapses down to reform the C double bond to O, and in doing so, it pushes this away, and so you end up making this. Okay, so you end up making this. You end up making the acetone. Now you say, well, that effectively is what happened. Is I added here and then just pushed that away. Yes, that is overall what's doing. But it's a good habit to go through the tetrahedral intermediate. This is important, for later on to think about the mechanism of it. Okay, so that is not just here and then pushing the chlorine away. They actually do go up and then collapse down and then kick away the chloride, or kick away your leaving group in this case. Okay, so after you do that first step, what you need to do is you need to look to see if you have a good leaving group, right? So if you have, because if you don't, then it's going to stop. It can't do that collapsing down step. Okay, so if you have, right, see if you have the methyl grignard, okay, remember that is just that. Okay, so this is effectively this. Okay, so again, you have a partial positive, partial negative. Okay, so these electrons are going to get attracted to there, right, and we're going to push these up. So you're going to make this. The oxygen is going to have a negative charge, right, and your methyl is going to be down here. Now, you look here and you say, okay, are there any good leaving groups here? Well, there's a carbon-carbon bond here. That's not a good leaving group. Same here and same here. You're not going to be able to break a carbon-carbon bond or a carbon-hydrogen bond in order to do this. You have to have something else on there, stuff like that. And so, if we can't move any further. So this is going to be our product. Okay, we're gonna have to stop there. So if there's no good leaving group when you get to this stage, you stop. If there is a good leaving group, okay, so like this chlorine here. Okay, so if there's a chlorine, a bromine, an iodine, something like that, okay, then you can collapse back down and then kick it away. Okay, because remember, leaving groups are designed to leave. If there's not a good leaving group, there's just carbon-carbon bonds, then you're cooked. All right, then you just stop. You're not cooked, but you just stop like this. Okay. Okay, so here we go. So if we have, put in the lone pairs plus, okay, this is our nucleophile, right? It's got all the lone pairs and it has the negative charge. So we're looking over here, right? There's a nice big fat polar covalent bond, right? So with that, especially this carbon is going to be pretty susceptible to that. So that lone pair goes there, right? You got to get rid of one of those bonds, right? So we're going to push it up here. That's the first step. Okay, so okay, and so we've turned in one of these pairs of electrons into a new bond, right? And that methyl group's just coming along for the ride. Okay, now we take a look at this carbon. Is there a good leaving group? Yep, there is. It's going to be that. So when this collapses down, this is going to kick this away, and so you're going to be left with this. Okay, plus the chlorine. This is the chloride. Okay. Now this bottom one here, Okay. Again, now this one's the lithium, methyl lithium, right? So again, this lithium is going to be there to stabilize the negative charge, but effectively this is again a methyl anion. Okay, so this is our nucleophile. Looking at the positives and negatives, right? So by that, so this is going to come in, react here, push those electrons up, so you're going to end up with this. Right? And then your methyl, okay? And where you attacked, you take a look, well, carbon, 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 carbon. None of those, it's not a good leaving group, so we're stuck here, okay? So there you go. Okay? Good luck.